Are there any questions before we begin from the previous lecture? You will not need to command it in the software. But you don't really have to implement it into software. Yeah. We do not focus on simplex because it would be too much. Yeah. So last time we were talking about branching bound. We have seen an example of it, and then we were talking about node selection. I think we covered. We said that there are two conflicting criteria in node selection strategy. On one hand, you would want to get like an upper bound, a tight upper bound for the solution, so that you can prune the nodes faster. By using pruning by bound. Therefore, it makes sense for you to pick a node to explore. That is being exploited in practice. And I believe we did take a look at the pseudo-cost branching last time, right? Did we speak about special order sets? I think so. We stopped on orbital branching, right? Okay. So yeah, the thing is, in some cases, orbital. So yeah, so in some cases, it makes sense to design like more sophisticated branching strategy than just branch by a single variable. And one of these cases is when our problem has some symmetry properties. It turns out that we are able to exploit this symmetry in order to solve our problem considerably faster. What kind of symmetry I'm talking about here is the symmetry among variables. So basically, we are talking about problems where if we switch the values of several variables, like specific subsets of variables, the point, like the value of the objective function wouldn't be changed at all, and like that new point after the switching of the variables will still be a feasible point in the problem. Consider the problem of let's put it formally. To put it formally, let's consider the maximization problem like let's say it's going to be a binary problem, but the same way we can define it for integer or mixed integer programming problems as well. A permutation pi like every permutation time the permutation can be represented with entry of 1 and all other entries being equal to 0. It's called a permutation matrix. We can define a set of column permutations for which there exists a permutation such that essentially the column permutation and the row permutation undoes the column permutation. So basically, implementing the permutation of rows over the matrix A and then doing the permutation of columns, or like the other way around, essentially, is that does not change your original matrix of your inequality matrix. And the same way, the permutation of rows does not change the vector B, the right hand side, and the permutation of columns does not change the vector C. Basically, it's a set of permutations. So G is a set of permutations that do not amend your problem at all. Are there any questions regarding the formalization? Is it, yeah? Oh. You will essentially end up with the same problem, right? Like they're literally going to be the same things. And the right hand side is not going to change, and then the vector of coefficients in the objective functions also will remain the same if you permute the variables. So essentially, this particular permutation of 1, 2, that brings 1, 2, 3 into 4, 5, 6 does belong to this set of permutations G. And this set of permutations G basically consists of all such permutations that basically leave the problem itself unchanged. We will look into more details into that example later. Okay, so we have a proposition that is saying that if a vector X satisfies the set of inequalities from our formulation, and a permutation pi does belong to the set G, the set of consistent permutations, then pi of X also satisfies the same set of inequalities, and therefore it's feasible, and its objective value is the same as the objective value of the original vector of X. This is quite clear. This really should be quite clear, because under the permutation pi, the vector of variable C shouldn't change. So the objective function itself should remain the same, and then since our entire problem was preserved under the permutation pi of variables, then Then we define the notion of orbit of a single single component J. An orbit is a set of all such components K. We would like to, so orbit of J is the set of all components in like to which J is similar to into which J can translated to by a good permutation, a permutation that preserves the problem. Is that clear? Is the definition clear? It's so basically, so this notion of orbit is like it's coming from the higher algebra where we have also permutations. Yeah, and then we have a proposition 7.4 that is saying that if so basically if your set of like preserving permutations G is not empty, then there is like for any I and for any J from the orbit of I, every solution X on the branch with Xi being equal to 0 and a permutation that puts, so this is, let's say that this is your vector X, and you have a permutation that exchanges Xi with Xj, or at least leads Xi into the Xj. Then when you're doing branching and you have a branch with Xi being equal to 0, and then somewhere here there is Xj being equal to 1, then there must be another, like also you have another branch that is having Xi being equal to 1 and Xj being equal to 0, and this node and this node will have the exact same problems underlying the nodes, and they will have exactly the same corresponding solutions. So you really don't have to solve both of these problems. Instead, you can just solve one of them, and then do not waste time on the other one. Therefore, it can save you time when you're trying to explore the branching tree. Is the idea clear? We'll take a look at the example right now. Is that of the overall idea clear, guys? We're good. Cool. So let's take a look at this example. We have an objective. So we have a problem with 6 variables. The objective function has the coefficients of 3 for the first 3 variable and has the coefficient of 2 for the second 3 variable. It also has the inequality of x1 plus x2 plus x3 being less than or equal than 2, has x4 plus x5 plus x6 being greater than or equal than 1, and then for all triples of variables such that I is between 1 and 3, j is j and k is between 4 and 6. and you can interchange x1 with x4. This will lead to this will lead to like the exact same problem essentially, right? And you can exchange with x5, x3 with a 6. And if you do this permutation, the entire form of the problem won't be changed, and the inequalities will translate into themselves. Permutation leads to exactly the same problem. If it's not obvious, I will definitely write it down. Like, can you raise your hand if it's obvious to you? I should. Okay, so let's say that x1 goes to x2. Goes to x4. X2 goes to x5, and x3 goes to x6. Start writing down. So we're writing down maximization of 3, summation of from j equal to 1 to 3. X. Okay, so now it's from 4. 6 xj plus 2 summation j from 4 to 6 xj, and then we write down x4 plus x5 plus x6 being less or equal than 2, and then x1 plus x2 plus x3 be being less than So this is the problem that we would get if we were to do this permutation, right? And then if we solve this problem, we will get a vector x1, x2, x3, x4, x5, x6, and we can just so it's gonna be stars. So we this is the solution. X star is equal to this thing, and then we can basically use the same permutation, or the actually it's going to be the inverse permutation. Essentially, notation should be used. Okay, so let's say that y is the solution for the original problem, and x is the solution for this new problem. Then y is going to be equal to phi minus 1 of x star, right? We just permute these components with themselves, and this the new vector is going to satisfy all of the constraints of the original problem, and also its value is going to be the same as the value of this vector. So the vector of y has the same value in the original problem as the vector of x star has the value in the new problem. Guys, did I confuse you? Because I feel I did. Yeah. What exactly is going to be happening branching? So in node 1, let's say so. Just a reminder what exactly we are doing during branching. So here I am assuming that we are working with bound algorithm based on the LP relaxation. The thing we are doing. In node 1, we solve the LP relaxation of, like, basically we just remove the binary constraint. We get this vector right here. Using the normal branching, then the first option is saying that x1 being equal to 1. The second option is saying that x1 being equal to 0, because it's just it's a binary thing. So in node 2, you would resolve this problem. You would get a solution of the LP being equal to 9, and then you have a new vector. And now you also need to do branching in this node 2. In the node 2, you can pick, let's say, the fourth variable to branch on, and you will get x4 being equal to 1 versus x4 being equal to 0. If you work through the node 3, you would get that you have again the LP having the same value of 9, and then you have also vector that is not integral. So you, let's say, again branch on the fourth variable, and you get x4 being equal to 1, x4 being equal to 0, just like here you had the same thing. And then you need to resolve all vectors of solve it even more. So like the next step, you will solve 8 more, and then 16 more, and that it would have a combinatorial explosion. And all of these problems would be essentially the same. In orbital branching, you would exploit the following idea. Basically, the first node is going to be would be essentially the same, but then instead of using branching on a single node, you can say that that you're okay. So you're still kind of branching on the same variable x1, but now since you understand that basically your choice, your branching here, the logic of your branching is whether all of the values x1, x2, and x3 at the same time can be equal to 0, because essentially you're using the permutation of this form x1 to x2 or x1 to x3. These two permutations will also preserve the structure of the problem. So basically, you can use these two permutations. In which form? Let me clarify on this. Basically, on this branching, you are your two logical kind of predicates that you're assuming is x1 or x2 can be equal to 1. Why is equal to 1. That and like this the same problem would well, so if x1 is being equal to 1, then after and like let's say that we have solved a problem with x1 being equal to 1. We have came to a solution. Let's say that we have came up with a vector where x1 is assuming that x3 can be equal to 1, then we flip x1 and x3, and the resulting solution is going to be the optimal solution for the case x3 being equal to 1. Just because this permutation that is just one example of this permutation. So potentially you could I don't think I used this particular example here, this particular permutation. So this permutation x1 to x4, x1, x2 to x5, x3 to x6. This permutation belongs to G. So this G of A, B, C, but also this permutation x1 to x2 also belongs to G. You don't have to use all of the permutations in G in order to do your branching. In this case, we just use this one. But potentially, you can use any of them, any of the permutations from G in order to do this. So were I able to argue that assuming that x1 being equal to 1 is equivalent to saying that x1 or x2 or x3 can be equal to 1? Is it clear that this is the same? Okay, cool. So yeah, so alternative to that is saying that none of the variables x1, x2, x3 can be equal to 1, which implies that x1, x2, x3 are all equal to 0, and that leads us to a second node, the node 3, for which we can also solve it exactly and get the lower bound and get an integral solution. So we don't have to branch the node 3 anymore. We just bounded by done in node 5. So you can see that to branch the node 1, we were using x1 and x2 being interchangeable, and x1 and x3 being interchangeable, and to branch node 2, we use that x4 and x5 are being interchangeable, and x4 and x6 are being interchangeable, which are two separate permutations, and both of them belong to G. Okay, cool.
So is it possible to do like one permutation from G that's used in another one? I was thinking maybe in the case where you can use x1 and x4 And will you be able to permute X2 then?
So say it again, the last part. The last part of the question. What exactly you're talking about?
Like when you're making all these permutations to simplify your
Right. Like not really, because permutations remain available, and this line of thought remains available no matter which node you're in. Yep. So you can even use reuse the same kind of the same permutations several times down the tree. For example, if we had more variables here, if we were not talking about binary problem, but let's say that x1, x2, x3 can take values 0 to 1 and 2, then this branch here would lead us only to say not like the alternative. So basically this would be saying that just one of at least one of the variables must be equal to 1 down the road, but we didn't say anything about having one of the variable which is being equal to 2, and so you would be you would still be able to say that you can still you could still, for example, have this branching further, saying that x2 is equal to 2, like on one end, and saying that I know x1 is equal to x2 is equal to x3 is equal to 1. Which is kind of another time that you can use the same permutation in order to simplify your branching, but in a different kind of. It's as a finite resource. Yeah. Does it make sense? Does it?
What you said.
Right.
In this case, you said you could permute x1 to x4. Can you is you're also able to x5 and x5 to x6?
Yeah.
You're able to permute x1 all of these 4, 5, and 6.
Yeah, that's a very good question, because I don't think I said it quite clearly. What I was talking about is permitting x1 with x4 at the same time as you permit x2 with x5 and x3 with x6, right?
Mm.
So you would need to do all of these permutations at once, and so it does you would never be able to permute x1 with x2 by themselves and keep the structure of the problem.
Okay.
Right? One of the most more complex things that people are doing. There are a couple more of interesting techniques. I'm not sure I'm talking about it here. Probably not. But yeah, it's you can read about this more. It's chapter 7. But I think we've covered most of it. Okay. Now let's switch to pre-solving. We were discussing before that different tighter formulation, something. These are two polydrops, and they are equivalent in this form, in this sense. And you say, and we have that P1 is a subset of P2, then P1 is better. And we already noticed that basically, if we have the best formulation, the best formulation ever that is better than any other formulation, then that formulation is tight, and we can use that formulation in order to just solve. We can just solve the LP relaxation of that for that formulation. That will give us the original problem. It's also extremely important to have better formulations, even if it's not very tight. Even if it's not perfect, it still helps in computation, especially if you are using especially with in the context of branching bound algorithm. So basically, branching bound algorithm will have less branching. It will converge faster if you have a better formulation. Therefore, there is a very big machinery in the IP solvers that is but we will start with an LP pre-solving, because this is the first kind of stage of any pre-solving procedure. So here we have a problem based on 3 variables with 3 different constraints, which are like complicated constraints, and then some bounds on the values of the variables. We need to try to get a better formulation. First thing that we can notice is that from the first inequality, we can obtain a bound on x1. Here's the bound on x1. Okay, here we go. So it's basically you just put everything that is related to x2 and x3 to the right hand side, and then you can use at least 1. Since x2 enters this inequality with a positive sign, and x3 enters this inequality with a negative sign, we can just substitute the upper bound on x2 and the lower bound on x3 into this inequality in order to obtain about inequality. Indeed, this is since it's a constraint from above, it cannot be higher than the constraint corresponding to the maximum value of x2 and the minimum value of x3. Does everyone okay? So after we substitute this, we get the value of 9, and therefore x1 is less than or equal than 9/5. So this is a new bound. Before we had x1 being less than or equal than 3. Now we realize that it's actually a better bound. This number eight x3 less and obtain that x3 just you can believe me that it's x1 greater than or equal than 7/8, and then from the once we have a better lower bound on x1, we can reconstruct a new upper bound on x3 by using the same first inequality and obtain that x3 must be less than or equal than 101/64, which is even better than the previous bound that we have had. Then the third inequality, for example, turns out to be redundant just because x1 plus x2 plus x3 is less than or equal than like if we just substitute individual bounds instead of x1, x2, and x3, we'll figure out that it's already less than 6, and therefore this inequality over here is like just not needed to us anymore. And increasing x2 this is something that I would like you to kind of tell me that it's obvious to you. So everyone who thinks that this statement is obvious, so I assume that everything else was obvious, and I would like just to ask you to raise your hand if you think that the last statement is obvious. Is it obvious? Is it not obvious? Not obvious? Okay, so let's take a look in more details. Let's take a look at these two inequalities, and let's take a look at the objective value. So here we are saying that increasing x2, let's see what is happening to the objective function and the gap in the first two inequalities. So we don't have to consider the third inequality anymore because it's redundant. So we only care about the gap between the left hand side and the right hand side in the first two inequalities, and the objective function. As we increase x, second inequality, and we increase the value of x2, the right hand side is going to be increasing, therefore it will increase the gap between the right hand side and the left hand side. Do you agree with me? Cool. And now the objective function, if you increase x2, will only be increasing by some. Right? So basically we can say that in the optimal like position, in the optimal solution, we will have x2 hitting its upper bound, right? Yep.
Should we be able to just see this and understand it when we get like a on the exam?
Well, if you can see it and understand, that would be great.
Okay.
But I really don't think like that will this is quite a complicated task. I don't think this specific task is going to appear on the exam or anything as complicated as this. And moreover, there is a more kind of algorithmic way of
So
This way, basically up in all of the constraints. Everything into this into this problem, x2 being equal to 1, x3 being equal to 1, you can just end up with a very simple formulation that is equivalent to the previous one, right?
Why you can ignore the third constraint? I know that x1 and x2 are bounded, but I don't see that x3 is upper bounded. So why is it that's for them?
You're asking why x3 is upper bounded?
No, so for x2, right? You can use 1 because for the first two constraints.
X3 is being less than or equal than 6. And then you can substitute the constraints, the upper bounds on x3, x1, and x2 into this expression right here, and get this expression.
And getting the upper, so for each one of them, you're calculating that.
Yeah, we already have them. So we have an upper bound for x3, and also we have an upper bound for x1, but a new better one. Here it is. And also we have an upper bound for x2 from the original problem, x2 being less or equal than 1. And so the left-hand side cannot be greater than this thing right here. And this thing right here is less than 6 already. So you really don't need to pay attention to that inequality anymore. Does that make sense?
Yeah.
Cool. Okay. Any other questions? Okay. So yeah, all of this, like all of this kind of techniques. So basically, we are saying that if we have a constraint that is saying that okay, if we have a set of constraints, and we have a constraint there that a0 x0 plus a summation of some linear function that depends on x is less than or equal than the right hand side, and also we have limits on the variables. Then we can consider several subcases and introduce new kind of new inequalities into the problem based on those cases. So first case is that a0 is being greater than 0. Then you can construct an upper bound on the value of the variable x0, and you can add this upper bound into the original problem that has this. Where aj is and lower bounds lj where aj is less than 0 leads to a number that is less than or equal than b, then the corresponding constraint the corresponding main constraint is a redundant one, right? This is what we did right here. And then there is there is a way to figure out that the set S itself is set if you just substitute satisfy this. Two are just the inequalities that can be added to any subset of inequalities based on one of the inequalities. Then like based on so this is called basically the you can relate to this as constructing upper and lower bounds on the variables, but also there is kind of like a constraint fixing, like a variable fixing philosophy. For that, you need to consider not just a set S, but a problem itself. For example, a maximization problem based on the objective value function as like Cx, with a set of inequalities Ax less than or equal than B, and X being bounded between the two values L and like between the two vectors L and K. And then if Aij is greater than or equal than 0 for all of the inequalities that participate in the main part of the constraint, and Cj is less than 0, then you can just safely assume that Xj must be equal to Lj. And like this, the last two options correspond to the last two cases that we have considered in the example. Do you want me to try to formally prove this, or is it okay? Good. Yeah. So basically, this this corresponds to the previous example. Now, since we have figured out how to do LP pre-solving, we can start doing things for IP pre-solving. So now we are talking about some integer variables, and the simplest idea, and actually the most powerful idea that there is the idea that you can round the upper and lower bounds on the values of the variables, getting valid constraints, basically constraints that do not restrict your set of feasible points in any way. So having a variable xj that has to be integer, and an upper and lower bound on this variable xj, you can safely replace this set of inequalities with this set of inequalities, where this ceiling of Lj is the rounding up of Lj, and the flooring of x like Kj is the rounding down. Like a four-dimensional we have the task of the x being equal to 0 leads to x3 being equal to 0, and also x1 being equal to 1 leads to x4 being equal to 1. Why is that? Well, if x1 is equal to 1, then basically and x4 are both equal to 1, because otherwise like this thing can only increase, this summand can only increase the left hand side, and the only things that can decrease the left hand side are these parts. And therefore we are saying that if x1 being equal to 1, then both x3 and x4 must be equal to 1. Equivalently, we can write down that x1 is less than or equal than x3, and x1 is less than or equal than x4. And these two new inequalities can be added to the first to the set of inequalities, to the initial set of inequalities. Are there any questions here? No? Cool. Also, the first row isn't feasible if x1 and x2 are equal to 1 at the same time. Therefore, x1 plus x2 must be less than or equal than 1. Like basically by the same and x2 and x3 cannot be equal to 1 simultaneously, just because this would lead to left hand side being having too great of a value. So we can add two more constraints that are not kind of obvious in the very beginning. From row 3, we can conclude that x2 and x4 cannot be equal to 1 simultaneously, and x3 and x4 cannot be equal to 1 simultaneously. Therefore, we can add these two inequalities here. And also x1 being less or greater than or equal than x3 is something that comes from the fourth inequality. Therefore, now that we have constructed all of this like additional inequalities, like are there any questions regarding how I constructed this? Is it obvious for everyone? Obvious, right? Okay, cool. Combination of pairs of logical inequalities is something that can help us in the actual simplification, because so far we were only doing complication of things. We were only adding more constraints. Now, from row 1 and row 4, we can conclude that x1 is less than or equal than x3, and also x1 greater than or equal than x3. Where is that? So x1 less than or equal than x3 is right here, and from row 4, x1 is greater than or equal than x3. Here it is, and therefore we can conclude that x1 is equal to x3. Then from row 1 and row 2, x1 plus x2 less than or equal than 1, and x2 is less than or equal than x1, which gives us x2 being equal to 0. So from row 1, we can conclude that x to 0. And also x2 plus x4 being greater than or equal than 1, and also x2 being equal to 0 gives us that x4 must be equal to 1. And after the substitution of this equations that we have obtained, the three main equations, we can conclude that there are only two feasible points in our set. It's the point 1, 0, 1, 1 and 0, 0, 0, 1, which significantly simplifies this expression to like just to the problem. So what we are doing here can be put together into kind of like a systematic way of like or how to say a more regular, more generic of doing things, right? Let's say that we have let's say that we have like a system of inequalities, ax less than or equal than b. Let's say that this is like it consists of a single inequality. So everything here is just numbers. All of the coefficients are just numbers, and we are talking about binary variables, but it's just for simplicity of understanding. But it doesn't have to be binary at all in general. First of all, I would like to say that for the purpose of this discussion, without the loss of generality, we can assume that ij is greater than 0, and then like everything that we state can be easily proven for aj being greater than 0. And what like basically why can I say that without loss of generality is because of the following. Separately over here, and then we can like basically we can add and we can subtract from both sides of this inequality this number, sum over all j such that aj less than 0 of aj, right? We just sum up all of the negative ajs, and then after we have done that, we can bound together all of the components that have like the coefficient aj, and then we will have the summation over all j such that aj greater than 0 of aj times xj minus summation over all such j's that such that aj less than 0 of aj times 1 minus xj, which is also by itself basically a binary variable. You can just say that this is some new variable xj xj prime or something like that, which is also a binary variable. And therefore you basically reduce the problem. And now this since this new thing enters this new inequality with the minus sign, now all of the coefficients in this new new problem are positive. So all of the aj's now are positive, and you have reduced your original inequality with the positive with the positive, both positive and negative aj's, to a new problem with a new right hand side, but all of the coefficients being greater than 0. So from now on, we can like at least for the next few slides, for the next slide at least, we can assume safely that aj are all greater than 0. Did I articulate it clearly? This than 0, then well, it doesn't make sense to include this inequality at all, and it is a redundant inequality, and we have x being equal to all of the binary numbers. If one component, one coefficient ak is greater than b, then obviously xk must be equal to 0. Otherwise, the inequality will not be feasible. If aj plus ak is greater than b, then we can add this inequality xj plus xk being less than or equal than 1, which is basically what we were doing, for example, here, or here, or here. So this is how we can like generalize this line of thought. If xj plus xk is less than or equal than 1, and xj plus 1 minus xk are less than or equal than 1, which is equivalent to saying that xj is less than or equal than xk, then xj must be equal to 0, which is exactly if xj plus 1 minus xk, which is basically saying that xj less than or equal than xk, and xj plus xk greater than or equal than 1, then xk is equal to 1. We didn't have this example right here. Oh, we actually did have it right here. It's basically over here. So we just said that xj is equal to 1, x4 is equal to 1. Yeah, so basically this is like a set of pretty simple kind of rules that formalize what we have done before, and being able to apply all of these rules systematically to a very large set of constraints can lead to a very good outcome. Okay, so this is like the very simple way of doing pre-solving. Are there any questions here? No questions, great. Now let's turn to a slightly more complicated technique, which is called the clique finding. Here we're gonna be using this notation saying that xi bar is equal to 1 minus xi, right? Here we are saying that first of all, just notice that, wait, do I have, did I skip the example itself here? Okay, no, never mind, it's all good. So we can take let's take a look at basically at this example right here. This is what we're gonna be working with. And x2 plus x4 less than or equal than x7 is the same thing as saying x2 plus x4 plus x7 bar is less than or equal than 1. Then we can rewrite this three inequality to this triple of if you think that this inequality by itself, this relationship is obvious. Okay. What about this one? Okay. what about this one right here? Not obvious. Cool. So x2 plus x4 minus x7 less or equal than 0. This is equivalent to the thing on the left, and then x2 plus x4. That's 4. Then plus 1 minus x7 less or equal than 1. I just added 1 to both sides, and then this thing is x7 bar, and therefore x2 plus x4 plus 7 bar is less or equal than 1. Qualities by that are equivalent to this to thing. And now the last part is to sum up these three inequalities in the middle. What we will get is x2 plus x4 plus x2 plus x7 bar plus x4 plus x7 bar plus less than or equal than 1 plus 1 plus 1, right? I just summed them up, and when I group it, x2, x2, x4, x4, x7 bar, I get x2, 2 of x2 plus x4 plus x7 bar is less or equal than 3, right? And then I divide it by 2 both sides. I get x2 plus x4 plus x7 bar less or equal than 3/2. And 3/2 is a fractional number, and it's right between 1 and 2. And we know that the left-hand side can only take numbers that are integer. Therefore, this left-hand side cannot take the value of 2 because it would violate the constraint, and therefore it must at least, like, the biggest value that this left-hand side can take is 1. Therefore, x2 is plus x4 plus x7 bar less or equal than 1. And then we just use this this third bullet that has right. Now, actually doing this by just doing this procedure is already an NP-hard problem, but again, you can exploit heuristics, and you don't really need to solve this NP-hard problem to global optimality in order to get a very good result and speed up the process of solution of your problem considerably. So let's say that we have a problem that is based on less than or equal than xj, and we connect xi bar and xj bar if xi plus xj greater than or equal than 1 is an inequality in our problem. Then what we do, we find a maximal clique in our graph. Do you remember what clique is? Okay. So if we have a graph, some other points probably, and we have some part that has all the possible connections between them, and like let's say that there are some other parts of are connected. A clique is a subgraph that is full, so it has connections between all of the nodes, direct connections. So for example, this 3 nodes, this and this and this, is a clique, just because from any node to any node there is a direct edge. And also this part, this thing right here, is also a clique, but it's a larger one. It has 4 nodes instead of 3 nodes. And a maximal clique is a clique of a maximal size. So it's a subgraph in a graph such that all of the nodes are interconnected. Okay, and so in this like imaginable graph, let's say that our maximal clique is C, but it doesn't really have to be maximal. It just makes sense to find up as big as possible. It consists of 2 parts. One part is C plus, and the other part is C minus, where C plus consists of nodes that correspond to variables themselves, and C minus exactly the same thing as we did before. So you will divide by will give you a valid clique constraint. So basically, this is another way of constructing another like a new constraint that is equivalent to all of the previous constraints that you have had, and it's actually a stronger one. So it has less. It's a way of strictly improving your formulation. This is some of the newer kind of developments, which is advanced technique than so it's an algorithmic procedure. Okay. Just demonstrate the proposition and also prove it, and then I will show you an example of how to use it to strengthen inequalities. So once again, the entire point of doing resolving is So consider like a variable w, which is non-negative, which takes non-negative real values, and the value the variable x that takes non-negative integral values. That's so the proposition consists of two parts. First, if a is greater than b greater than 0, then an inequality of this form, w plus ax is greater than or equal than b, is equivalent to the inequality saying that w plus bx is greater than or equal than b. Let's take a look at how to prove this. First, so this is our initial inequality. This is equivalent, since we are saying that a is greater than b greater than 0. This is equivalent to saying that either w is greater than or equal than b, or x is greater than or equal than 0. Oh, sorry, than 1. It cannot be, x cannot be equal to 0 if w is less than b, and the other way around. Basically, so basically one of these two conditions has to hold. And this kind of choice between the two conditions can be written down as w plus bx is greater than or equal than b. And this inequality over here is in fact a better inequality, a stronger inequality than the original one, just because this value b is smaller than the value x, the value a. Did I is it obvious what I just said? Let's stop on this for a second and think about it. If there's, yeah.
So that x is greater than or equal to 1, that's presented as a is required.
Right. Yeah, because if you substitute then it would be sufficient then that x is equal to 1. Like saying that x is equal to 1 is sufficient for this, like for the entire inequality to hold. But if x is equal to 0, then w has to be greater than or equal than b. And this is something that is satisfied. We have some upper bound on the value of w. It's still a non-negative real number, but now we have an upper. And like the alpha, which is to be greater than 0. So this is a notice that here we had greater than or equal than b, and here we have less than or equal than b, which is it's a different equality. So this inequality is equivalent to the inequality saying that w plus alpha x is less than or equal than capital W plus alpha times k minus 1, which is, it turns out that it's actually a better inequality just because this alpha is smaller than a, and also this thing on the right hand side is, but like it's basically, it's better to have that instead of having just b. To prove this, we will need to refer back to the first bullet. So let's take a look. so first of all, we did assume that alpha, which is defined this way, is greater than 0. And it is in fact a necessary condition for saying that the problem is non-trivial, because if this condition doesn't hold, then after substitution, the upper bounds into this inequality, like instead of just the normal W, we would substitute the capital W. Like instead of the W plus AX less or equal than B, we substitute the capital with W, and then we substitute the K, and then we say that this thing after we substitute, like basically saying that saying that alpha is less than 0 is equivalent to saying that this thing is less than B. And if this thing is less than B, then it's not clear why we would consider this inequality at all, because it would be trivial, just a trivial inequality that would hold for all the variables of the values of W and X. So we wouldn't be thinking about this problem at all. So basically saying that alpha is greater than 0 is something very, very the X bar is the gap between bound K and the value. So this thing is equivalent to saying that okay, yeah. So basically, we are saying that the first bullet. This is where we use the first bullet of this proposition. So this thing is a this condition equality to this one. Is it clear? Variables, we will get this expression, which is equivalent to this expression over here. And now the thing that we still need to think about is why do we think that this this inequality on the left hand side is true? So we like the chain that we have constructed is that if this inequality is true, then this inequality is true, and then this inequality is true. Moreover, it's all these inequalities are equivalent. So this inequality is equivalent to this inequality and equivalent to this inequality. But why did we think about this inequality to be important at all? This first inequality. Let me clear it up a little bit because it's not even clear which variables participate in this. Okay, so why did we think about this first inequality at all?
It's like the first bullet.
So yeah, so this inequality looks like the inequality in the first bullet, right? We have put it into this form, but actually this inequality is exactly this inequality right here. If you just substitute instead of W bar, you substitute the definition of W bar. If instead of X bar, you substitute the definition of X bar. Instead of alpha, you substitute alpha, and then you cancel out everything, you will get this. Therefore, this thing is equivalent to this thing is equivalent to this thing, and this thing is equivalent to this big thing. And this big thing is equivalent to this. Right? Once again, let me draw it as a graph. So this thing is equivalent to this. And this is equivalent to this. And this is equivalent to this entire. Doesn't think that it's obvious. Problems. So this is something. This is the first case when we are talking about something. Let's integral non-negative. Y1 has some limit. Right? They are not even non-negative. It doesn't really matter in this case. So right, the thing that we need to make sure is that it's non-negative. And in fact, since our Y1 is upper bounded and Y2 is like will be obtained if we were to introduce, to basically substitute the upper bound instead of Y1, the lower bounds instead of Y2 and X1. This would lead us to a value of 20, which is the value of capital W from the proof that we have had on the previous slide. So the capital W in our case is equal to 20, and A is equal to 12, and alpha is equal to 2, just by substituting everything into the expression for alpha. Why is A equal to 12?
So it's W plus AX and W.
Right.
And so the 4 times 12 is 2, so A is 12.
Right. Yeah. Okay. Great. So let's define the W bar, which is 20 minus W, and X2 is 3 minus X2, which is the upper bound on X2 itself minus X2. So our K is equal to 3. Then we can just write down the expression for so we can write down the expression W bar plus AX bar plus greater than or equal than alpha. Here it is. And that is equivalent to the original expression, first of all, and also it is equivalent to the expression saying that W bar is plus 2x2 bar is greater than or equal than 2. So instead of this 12, now we can put down 2, just because of this this entire statement. This 54 that we had before. By using the strengthening procedure, we have obtained this stronger inequality. We will further consider the valid linear inequality pi x less than or equal than pi 0. That for all added without any direct consequences, but oftentimes, so like basically in a more rigorous way, and then we will try to construct an algorithm that is based on constructing this valid inequalities. So tomorrow during the discussion section, I will consider more examples regarding how to construct valid inequalities and stuff like that. But I think for now, I will stop right here, and let me know if you have any questions. See you all next week.